So in our today's class, we are dealing with the capacitors. Right. So what exactly we are speaking about? So when I am using the word called a capacitor, in fact, I am referring to a combination, a combination of two conductors, a combination of two conductors placed close to each other. Remember, they should not touch each other. This arrangement is called capacitor. Combination of two conductors placed close to each other is what we call, that arrangement is called capacitor. Here, one of the conductor, okay, is given positive charge. Say Q. And the other will be given negative charge. Please try to understand, the charge on the positive plate is what we call as positive plate or positive conductor. You call whatever you want. Charge on the positive plate is usually referred to charge of conductor or capacitor actually. But please remember, net charge is always a zero. Net charge is always a zero. Why? Because whatever the positive amount you are giving to, say, some A, like for example, you take a conductor A, you take another conductor B, you have given plus Q to this, and you have given minus Q to this. And it will have some potential V plus, and it will have some potential V minus. So net charge is always zero. Arrangement, for the arrangement, it is zero. Also, the potential difference V plus minus V minus, right? And this term is called potential of a capacitor. So that is the introduction to capacitor. You are speaking about a combination of two conductors which are placed close to each other. And one conductor out of both, here say for example, A is given positive charge and B is given negative charge, right? And in general, when I am speaking about the charge on the capacitor implies I am speaking about the charge on the positive plate, right? But net charge is always zero. When I am speaking about the potential of the capacitor, I am speaking about the potential difference. Remember, the entire arrangement, every time you cannot write. So symbolically, we will represent it like this. Like this. Some books, they will represent it like this. Here the curved part represents positive plate. But I am telling you, throughout the chapter, I am not going to use the, what do you call, the second arrangement. I will use the first arrangement. I am not going to use the second arrangement, right? But one thing is very clear. Whenever you are giving charge to a capacitor, the potential difference between the arrangement or between the conductors will increase. So therefore, charge given to a capacitor Q, right? It depends on, it is proportional to the potential difference. You keep on giving charge, the potential keeps on increasing. It is as same as take a glass, a long glass, transparent glass for a while, pour some water in this. The amount of water you pour into that particular glass will be proportional to the height achieved in that capacitor. You keep on pouring, the height keeps on increasing, but at some point of time, you will reach full capacity, and thereafter, whatever the charge you give, it will, whatever the water you pour into the glass, it comes out of the glass and comes into the surroundings. Even capacitor, it will have a limit. Arrangement also will have some limit. So therefore, the proportionality constant is represented by a term called C. And this C is called capacitance of the arrangement. Remember, don't get confused. I am using a new word called capacitance. Capacitance of a capacitor. Capacitor is an arrangement. Capacitance is the measurement. And remember, it depends on shape, size, and geometrical arrangement of arrangement of A with respect to B. I think you got what are A and B here, conductors. And also on the nature of medium between them, right? And therefore, C is a physical quantity. You should express some units. So the SI unit, we are worried about only SI unit, is called, you usually use farad or symbolically capital F. Actually, farad is a very big unit. We will use microfarad, nanofarad, picofarad. 1 microfarad, 1 μF, microfarad is 1 into 10 power minus 6 farad. 1 nanofarad, 1 into 10 power minus 9 farad. 1 picofarad is 1 into 10 power minus 12 farad. I think you got my point. Right? Any doubt till this point? Pakka? So I have introduced what exactly is a capacitor. Right. Earlier, they used to call this as a condenser. After Second World War, mostly they are calling it as a capacitor. Generally, electronic devices, we will use a capacitor. Electrical devices, fan, motor, etc., like kind of thing, we will use condenser. So don't get confused between condenser and capacitor. You are speaking about the same thing. Right. Now, The first point is we will have different types of capacitors, but I'll just introduce you first parallel plate capacitor. Just introducing you parallel plate capacitor. See, what is a parallel plate capacitor? Very simple. You will have two plates. It can be a square plate, rectangular plate, or circular plate. Makes no sense. You will have two plates like this. They were separated by distance d. Each plate is of area A, and they are separated by a distance d. Now, what you have done, you have given some charge to these plates, plus Q and minus Q. See, at the edge, we won't consider anything at this point of time. Right. Now, we assume the electric field in this region normally uniform. Deep inside, normally uniform. At the edges, it is a different thing, which I will discuss in my next week class. Right? Dielectrics class. But for a while, we assume that it is a uniform. So what is the potential difference between these two plates? It is nothing but electric field into distance between them, since it is uniform electric field. From Gauss law, we know the electric field inside is Q by epsilon naught A. Yes or no? Into D. So therefore, I can write now Q as epsilon naught A by D times delta V. How it looks like? Q is proportional to delta V. So the proportionality constant is epsilon naught A by D. Remember, this is the expression for capacitance of a parallel plate capacitor with air as a separation between the plates. This is the expression for parallel plate capacitor, and I am not touching anything beyond this at this point of time. This is what I wish to introduce, because a third class or second class down the line, I will discuss different varieties. And during dielectric, I will give you a different varieties. Right now, parallel plate capacitor means only this. Effective area of sharing, A here represents. Next, spherical capacitor. I'll discuss that one also. Spherical capacitor. Before I discuss spherical capacitor, till this point, any doubt? Every student in this class. Now, spherical capacitor, you have a spherical capacitor like this. Right. So now what is happening here? Try to please understand. You require this is a spherical capacitor of radius A. D. Now try to please understand. I am giving some plus Q charge to here. For a while, I am assuming this is earth end. Obviously, you will have minus q charge here. Any doubt till this point? Right. Now the question, because the sharing part, whatever the field lines emanating out from the surface of the inner sphere ends on the inner edge of the outer one. Now, you know what is the potential of the inner sphere. It is nothing but 1 by 4 pi epsilon naught q by a minus 1 by 4 or plus 1 by 4 pi epsilon naught minus q by b. What is the outer one? 1 by 4 pi, yes, it's exactly 0 because you have connected to earth. Now tell me what is the expression for potential difference here? 1 by 4 pi epsilon naught q times 1 by a minus 1 by b. So therefore, q is equal to 4 pi epsilon naught delta v times 1 by a minus 1 by b. Got the point? Now the question is, what do these constants stand for? What do that constant stands for? It is the capacitance of the arrangement. So therefore, the capacitance of the arrangement is 4 pi epsilon naught 1 by a minus 1 by b. As b increases, say b tends to infinite, what happens? C will become a 4 pi epsilon naught a. This is called capacitance of isolated spherical conductor. Capacitance of isolated spherical conductor. Any doubt till this point? So what I am doing, please try to understand. I am trying to find out the potential difference. And I am trying to find a relation between charge and how is it related to potential difference. Till this point, any doubt? Very clear? Now, what if you take another combination like this? What if you take another combination like this? This is the spherical conductor. Of course, this is another spherical conductor. The only difference is you have in earth and the inside. And you have given a charge plus Q to this. Remember, you have already done these models earlier, electrostatics of conductor. You will have some Q1 charge here. That is not at all a matter for me. What is the potential? What is the potential of the outer one? No, before that, potential of the inner one is 0. That you know. So which means 1 by 4 pi epsilon naught q1 by, this is A and this is B. q1 by A minus q by B. Oh, 1 minute. q1 by A plus q by B is 0. So which implies q1 can be taken as minus A by B times q. Hold on. That is not what we are worried for. So what we are worried for is VO outside. This is nothing but 1 by 4 pi epsilon naught 1 by 4 pi epsilon naught. Hold on. Why? The charge is Q. That's all. You have given charge Q. The net charge. Why Q plus Q1? Tell me. Tell me. You are speaking about the induced charge of minus Q1 inside and plus Q1 outside. Both will get cancelled. What is the net charge and the outer shell? It's Q. That's all. So Q by P plus Q1 by P. That is the potential of the outer one, which is nothing but 1 by 4 pi epsilon naught Q by B minus, by proper substitution, you will get minus AQ by B square. So this can further be written as Q by 4 pi epsilon naught B minus A by B square. This is the potential of the outer shell. Potential of the inner shell is 0. Now tell me, what is the potential difference? The potential difference is nothing but Q by 4 pi epsilon naught B minus A by B square. Now I am rewriting this as 4 pi epsilon naught by B minus A by B square times delta V. Now, what do you comment about this constant of proportionality? This constant of proportionality is the capacitance of the arrangement. Look-wise, both are same. A inside B, but they have different capacitance. Why? Because arrangement of the first case is different from the arrangement of the second case. In the first case, you are giving charge to the inner. In the second case, you are giving charge to the outer one, right? So therefore, C is 4 pi epsilon naught B square by B minus A. This is the expression for capacitance of the arrangement. Capacitance of the arrangement. Okay? Right. These are two different cases. Right. Now what? Any doubt in this part? Please just confirm. Any doubt in this part? Right. No, one should need to identify that. You must have an idea of why this is equal to 0, because this is connected to ground. One must have an idea on this. Are we clear now? Okay. Right. Now, series and parallel combinations. So I'm just doing first level introduction of these topics to you. Thereafter, we will proceed for higher order models. Next. Series and parallel combination of a capacitor. First, try to understand how you will charge a capacitor. Now you have a capacitor like this. Basically, you have a capacitor like this, and you will have a battery cell connection like this with a switch. Now you see this is, once you close the switch, once you close the switch, this is open, no charge here. Notice there is no charge on these plates initially. Once I close the switch, it gets charged. Okay, a positive charge. Actually, what happens is electrons will move in anti-clockwise sense here. Like for example, you take this as plate A and this as a plate B for a while. Electrons will move from the negative terminal of the battery to B. An equal amount of electrons of plate A will reach the positive terminal of the battery, which means If you see actually what is moving externally is electrons. How long this will take place? Instantaneously this will take place. Instantaneously. Which means, suppose if this is potential V, EMF of the cell is V, for example. In no time, you will get negative charge minus Q on this plate and positive charge plus Q on this plate. This is how you will charge a capacitor, and it's instantaneous. Now, Q is nothing but CV. This is the fundamental way of charging a capacitor. Right. Now, what happens when we connect capacitors in series? Now, in series connection, what is happening? I have connected it like this. Now, say a charge Q flows throughout the circuit, and it is the same charge that passes through each capacitor, or it is the same charge that each capacitor will have. Like, for example, I am taking this capacitance as C1, C2, C3. Now, what is happening here? You will have plus Q, minus Q, plus Q, minus Q, plus Q, minus Q. Since they are different capacities, A, B, C, D, VA minus VB becomes plus Q by C1. Yes or no? Yes or no? Now, VB minus VC becomes plus Q by C2. VC minus VD is plus Q by C3. Now you take all the summation. VA minus VD is nothing but Q times 1 by C1 plus 1 by C2 plus 1 by C3. But that is nothing but the potential difference across the terminals of the cell, which you will call as EMF of the cell. Now this is V is equal to Q into and 1 by C1 plus 1 by C2 plus 1 by C3. Suppose if the entire arrangement is replaced with one single capacitor whose capacitance is CS and whose EMF is V. I would have written V as simply Q by CS. Right. So this is equation 1 and this is equation 2. So comparing, I can write the series equivalent is 1 by C1 plus 1 by C2 plus 1 by C3. This is the expression for series equivalent of a capacitor. So in series, points to note is charge is same, no splitting of charge. Wherever you see splitting of charge, you see that it is a parallel combination. It is splitting happening, it's not a series at least. Charge is same. And the total potential difference is, doubt unte nanu kadra adagalu. What is your doubt? Why you should take reciprocal of that? Tell me one reason why you should take reciprocal of that. Tell me, man. What are you listening here? What am I teaching? What are you listening? Now, what will you store in your mind? Even the teacher is teaching, you are not in a state to listen properly. You are not in a state to take data properly. It's such an idiot mind. How you will remember all these things while you are doing the exam? Now tell me one reason why you should take reverse. Tell me. I have reason. I have given you fundamental. Potential difference is charge by capacitance. Now tell me how, what makes you, what law allows you to write charge into capacitance? Do you have anything? Then shut up and listen to my teaching. V is V1. No, you know why you will fail in understanding that? You will not listen to what I am teaching. You will feel something else related to that. You neither have a knowledge on this part earlier. If even exists, that is a poor knowledge. Rather, you format that, let it installed freshly. You are not allowing that. Charge is the same and potential difference is sum of V1 plus V2 plus V3. And please remember, since Q is a constant, C1 V1 is equal to C2 V2 is equal to C3 V3 is equal to Q, which clearly indicates V1 is 2, V2 is 2, V3 wherever you require, simply follow this ratio. This is all about series connection. Any doubt till this point? Even at a fundamental level, I am prepared to answer. Even at a fundamental level. Any doubt till this point? Pakka? Right. Next. Parallel combination. See, not necessarily every time you take a circuit, you will have strictly series and strictly parallel. You take a circuit, you will have a different combinations. What I am teaching you now is fundamental. So what happens in a parallel combination? In a parallel combination, you will have an arrangement like this. So you have three capacitors connected like this, C1, C2, C3. And now I am connecting the entire arrangement to a cell whose EMF is E. Now a charge Q was driven by the battery. Now this charge reaching at this junction will split into Q1, Q2, Q3 because they are different capacities. They are of different capacities. Three different tanks, different capacities. Q1, Q2, Q3. And thereafter they will merge and return back as a Q. That's how you will just represent a cycle. Now in this case, what is common to each capacitor? Potential V is common to each capacitor. So when someone asks me what is a Q1, I will simply write C1V. Someone asks me Q2, I will write C2V. When someone asks me Q3, I will write simply C3V. And don't forget, law of conservation of charge says Q is equal to Q1 plus Q2 plus Q3. Q is equal to Q1 plus Q2 plus Q3, which implies this is a C1V plus C2V plus C3V. And this is a Q. Suppose if you represent the entire arrangement with one single capacitor, whose capacitance is a CP, equivalent parallel combination. I would have written that as a CPV, C1V plus C2V plus C3V. So therefore CP is C1 plus C2 plus C3. This is the expression for parallel combination. So what is common? Potential difference is common. So how charge Q1 is to Q2 is to Q3 takes place? C1 is to C2 is to C3. This is how it takes place. And this is what we call about parallel combination of capacitors. Now tell me till this point, do you have any doubt? I am repeatedly telling you where we will do mistake. We will do mistake in proper learning. Suppose you have any doubt and you are compromising now, what will happen? This will create a big vacuum in your mind and it will not allow you or let you to do problems freely later state. Till this point, are we clear? Right. Next, let us start doing this question. You have two capacitors having capacitance C1 and C2, and they are connected in series to a cell of EMF V. Find the charge on each capacitor and potential difference across them. The charge is common. So which is, now try to please understand. I need to convert this into a single series equivalent capacitance for which Q charge flows. I know 1 by Cs is 1 by C1 plus 1 by C2. So therefore Cs is C1 C2 by C1 plus C2. Therefore the charge is CSV. So C1 C2 by C1 plus C2 times V. Done. They are not asking that. What is that they are asking? Now the potential difference. So Q is C1 V1. Therefore V1 is Q by T1. So this will become C2V by C1 plus C2. If you are asking me V2, I will write Q by C2. This will become C1V by C1 plus C2. So simple numerical to understand what's happening over here. Any doubt in this? Next. Next point. Next point. In the circuit shown in the figure, find the, now you, why don't you try this? In this case, this will become equivalent circuit. This will become equivalent circuit. So in this particular question, you see, this is how I have modified the parallel part to a single 5 microfarad capacitor. Now this is your regular circle. V1 is to V2 is 1 by C1 is to 1 by C2. Means 1 by 1 is to 1 by 5. This is nothing but 5 is to 1. Right. So therefore, how to break 60 volts into 5 is to 1? V1 clearly becomes 50 volts. V2 clearly becomes 10 volts. What do you want? Equivalent capacitance between point A and B. Okay, first that I can find. What is the equivalent capacitance between A and B? 1 by Cs is equal to 1 by 1 plus 1 by 5. So implies CS is equal to 5 by 6 microfarad. The nature of mistakes which you will do is units. Just please take care of that. And by the way, charge on each of the three capacitors. Now I know here the voltage drop is 50 volts and here it is 10 volts. So therefore, the charge across AD part or charge at 1 microfarad capacitor. 1 microfarad is CV, 1 into 50, 50 microcoulomb. The charge across 2 microfarad capacitor is 2 into 10, 20 microcoulomb. The charge across 3 microfarad is 3 into 10, 30 microcoulomb. Any doubt till this point? Right? So now let us proceed to the next question. Remember, in a circuit of this type, it's closed. Now you see, you can take that this is 0 volt. The potential drop across both the capacitors is 30 volts. That doesn't mean only drop across AC is 30 volts. If B is taken as 0, the potential of A is 30. Means across AB, the potential drop is 30 volts. No, what is that you need to do is the potential drop across here is V1 and the potential drop across here is V2. Can you please help me? How is 2 and 3 connected? Series. So therefore, V1 is to V2 is 1 by C1 is to 1 by C2. 1 by 2 is to 1 by 3. Multiply with 6. 3 is to 2. 3 is to 2. Now, how to break 30 volts into 3 is to 2? V1 is 3 by 5 times 30. 18 volt. V2 is 2 by 5 parts of 30. 12 volt. Done. What is the find the potential of C? Here VC minus VB is 12 volt. You know VB is 0 volt. VC minus 0 is 12 volt. Therefore, VC is 12 volt. Not only that, you can find charge on any of these capacitors because you have potential drop across each capacitor. Till this point, any student having doubt? Honestly, right? Now, the next part of my discussion will go like this. Now, you take an arrangement like this. You take an arrangement like this. Here you have two spheres of radius r and radius 2r having charges. You can see having charges. One is q by 2 here and the other is q here. Understood? Now the question is, now read the question. When the switch is closed, see, so long the switch is not closed, remember, no charge flows actually. So long the switch is not closed, no charge will flow actually. And sir, I am very confused. How to handle such questions? What nature of circuit this particular thing will go with? Now, I see that, now for example, I see that suppose if once they were connected, okay, I should see the arrangement like this. Or I should see the arrangement like this. because the other one is at infinite distance, spherical capacitor. And remember, when I am drawing as an arrangement like this, 2r have nothing to do with the r radius sphere. So what will happen? It will send some, no, finally say the charge on this is q1 and the charge on this is minus q2, because polarities are like that, right? Now, how you will manage this particular thing? Now, if I take this arrangement, I will take this as A, I will take this as B, I will take this as C, I will take this part as D. Any objection till this point? I'm confidently asking you. What is VB minus VA? Everyone in this class will answer this wrong. I'm very confident. What is VB minus VA? I said everyone will answer this wrongly. So actually, this is minus Q1 by C1. In fact, VA minus VB is Q by C1, Q1 by C1. Next, VA minus VC is the V, V, V. And VC minus VD is minus Q2 by C2. Remember, there is no confusion. Wherever I have C1, I will write this as 4 pi epsilon naught C1, 4 pi epsilon naught 2R. Wherever I have C2, I will write this as 4 pi epsilon naught R. Just now I taught you spherical capacitor. Right. Now take the sum of all these things. In fact, VB minus VD is 0, connecting both the earth. Therefore, this will become minus Q1 by C1 plus V minus Q2 by C2. So therefore, Q1 by 4 pi 8 pi epsilon naught R Q2 by 4 pi epsilon naught R is V. So therefore, Q1 plus 2Q2 is 8 pi epsilon naught R V. Remember, that is the equation. Got the point? But here charge is conserved. Why? Because charge is conserved. No leakage to the space. So actually, 8 pi epsilon naught. What do you want finally, by the way? What is that there? When I switch finally, find the final charge on each sphere. Right. No issues. So what is the total charge of the system? Actually, what was the total charge initially on this system? Before you connect you have plus Q charge over here. You have plus Q by 2 charge over here. So on this arrangement, on this particular arrangement, net charge is 3Q by 2. which means wherever I have Q1 plus Q2, actually Q1 minus Q2, because you have committed that this is a negative charge here. Already, you can see there, Q1 minus Q2 is 3Q by 2. Whereas you have one relation, Q1 plus 2Q2 is 8 pi epsilon naught RV. Okay, fine, no issues. Now we will call this as equation 1 and this as equation 2. 2 times equation 1 plus equation 2 we will take up. In that process, Q2 gets cancelled. So you will get 3Q1 is 3Q plus 8 pi epsilon naught RV. So Q1 is Q plus 8 pi epsilon naught RV by 3. Boys and girls, any doubt? Sure. Next. Now you substitute this in equation 1. Equation 1 implies Q2 is Q1 minus 3Q by 2. And this is equal to Q plus 8 pi epsilon naught RV by 3 minus 3Q by 2. So this will become 8 pi epsilon naught RV by 3 minus Q by 2. That is Q2. Now please tell me, now if you ask me this plate as A, this plate as B, right? And this plate is A, and this plate is B. A is your actual sphere. On sphere 1, charge is, tell me, you committed it as a Q1, which is nothing but Q plus 8 pi epsilon naught RV by 3 on sphere 2. Charge is, here we will do mistake. If you write Q2 wrong, minus Q2. So this will become Q by 2 minus 8 pi epsilon naught RV by 3. Remember, here you may do mistake. I am telling you where you might do mistake also. But if you say that in exam that I have done a silly mistake, means that is not at all acceptable. Right. Now I have done this problem in elementary level. Elementary level. Any doubts? Pakka, everyone in this class. You have any doubt? Ask me right now, no issues. So what I have done, I have clearly informed stepwise. Right. So what's all they asked? When the switch is closed, find the final charge on the each sphere. Right. Next. Now, hold on. I will discuss some more models. 1 minute. I'll discuss some more models. Only then I will go for I need to discuss some more models. Right. This is a very good model. Irido model also. Same question you can expect in Irido model also. Actually, we have such a model in Irido where the language of questioning is slightly different. The language of questioning is slightly different. Both are same questions actually. Both are same questions. So therefore, I will approach two conducting spheres of radii A and B placed at a separation much greater than their radii. In that case, you can take them as 2-point charges. Now this is radius A, and I am assuming this radius B. Right. And D. Right. Now, on this, what is the potential? I am assuming that, please come to the original definition of capacitor, please. Two conductors. You have seen two conductors. One is given plus Q, the other is given minus Q. Right. Now, what is the potential of the positive sphere? I will write this as 1 by 4 pi epsilon naught Q by A. Agreed? I will write this one as 1 by 4 pi epsilon naught Q by B minus Q by B. Agreed? Can someone please help me in writing what is the potential difference in this case? V plus minus V minus. So this will become 1 by 4 pi epsilon naught Q times 1 by A plus 1 by B. That is the potential difference. I hope till this point you have no doubt at all. Till this point. Paka? Right. Now, what exactly this is the potential difference, right? When they were largely separated, right? If D is very high, I mean, potential difference is that is how you will take. If D is a considerable amount, then you should not take like this. For example, if D is a considerable amount, not infinite, then what will happen? You should modify this as on the surface, you will have 1 by 4 pi epsilon naught Q by D. Yeah, the interreaction of the right side one on this plus 1 by 4 pi epsilon naught Q by D. Right. Now, in this case, this is incomplete. This is not correct. I am taking D finite, not infinite. In that case, what will happen is minus 2 by D. That will be the potential difference. If D is very high, infinite, or D is negligible, then obviously it will become 1 by A plus 1 by B only. Any doubt till this point? Am I confusing you in rewriting V plus and V minus? I did not cheated you. Remember, if D is infinite, only first terms are sufficient. If D is considerable but still much greater than A and B, that is how you need to write. Right. Now you have potential difference. Now you have capacity. C is 4 pi epsilon naught by 1 by A plus 1 by me minus 2 by D. If D is very high, you neglect 1 by D in comparison with 1 by A plus 1 by B. Right. Now what they are asking, one more point here. Find the electrostatic energy U of the system and calculate the capacitance of the system. I have given you capacitance. What is the energy? The energy of the system is two things, U1, U2, U3. What is U1? You already studied electrostatics, electrodynamics. What is the energy of the first part? The energy of the first part is Q square. Q square by 8 pi epsilon naught A. The self-formation energy of the other is 8 pi epsilon naught B. And interreaction energy minus Q square by 4 pi epsilon naught D. So that is Q square by 8 pi epsilon naught. If I take a common, then what I am going to have is 1 by A plus 1 by B minus 2 by D. That's it. That is the expression for total energy. Whereas if it is an irido question, if I wish to separately do this again, if I wish to separately do this again, for a while you forget about the medium and all that. B is much, much, much greater than A. In this case, you will consider the potential difference strictly as, in this case, the potential difference strictly as Q by 4 pi epsilon naught 1 by A plus 1 by A. Here, two are identical. This will become Q by 2 pi epsilon naught A. That is the potential difference. So Q is 2 pi epsilon naught A delta V. Right. So therefore, that 2 pi epsilon naught A is the capacitance if medium is air. Otherwise, I would have written 2 pi epsilon naught, epsilon A as the capacitance. That is Irido's question. Any doubt in this? Right. Let me just see any other questions which can be solved right now. Just hold on. Huh? Of course, we have series parallel, and I will take up one more topic right now so that I could initiate maximum possible models. So in this, I am introducing a concept energy stored in a capacitor. In this case, now you have a capacitor, battery, whose EMF is E, and this is capacity C. Now you charge. Now in this process, at some instant, let Q be the charge on the positive plate and minus Q be the charge on the negative plate. And you are charging this further dq. In this, I need to do work. Why? Already there is a potential difference of Q by C. And you are doing work by this much amount. Yes or no? This, at this instant, on the capacitor, you are doing this much work. Now, all such works, if you add, total work done on the capacitor will be Q square by C, where Q is CV. This you can write it as C square V square by 2C or CV square by 2. Remember, this is stored in the capacitor in the form of energy, potential energy, and actually that energy will be electric field energy. You have the plates like this, positive plate, negative plate, you will have electric field like this. So this energy is stored between the plates in the form of electric field energy. So a capacitor stores electric field. In a resistor, you will see heat. In an inductor, upcoming topics, magnetic field form. So these three are very important. In a capacitor, energy is stored in the form of electric field. By the way, for this, what is the work done by the battery? Battery transfers a Q charge across the plates which are maintained by a potential difference of V. Of course, I should say E because E is the EMF. Right? Instead of rewriting this much times, better we erase this E and replace it with V. Otherwise, I need to change it number of places. QV. That is the work done by the battery. Q is CV square. Please try to understand your battery have done a work of CV square. Your battery have done a work of CV square, notice here. Whereas the energy stored in the capacitor is half of this, which means in this process, half CV square energy is lost. This part which you cannot account generally, we will post it in the account of heat. Dissipated, I should say, dissipated. This much amount of energy is dissipated, lost. Any doubt? Now the question is, okay, fine, you have charged a capacitor to a battery. You can charge a capacitor in a different way also sometimes. Already charged capacitor can charge another capacitor. That is also there. Like, for example, charging a capacitor with another charged capacitor. Which means you have a capacitor of capacitance C1 with charge plus Q. Now you have closed. You have closed the switch. Then what happens? Sharing of charge takes place. Any doubt till this point? So what will happen finally is this capacitor will lose some charge. And this capacitor will gain charge. When you are writing plus Q, you should account the same like this. Please remember charge is conserved here. And they will attain a common potential also. What is the common potential? Total charge by C1 plus C2. Yes. Because finally this is the common potential. Till they attain common potential, charging takes place. Once the potential drop across C1 is same as the potential drop across C2, charge flows. Once common potential is arrived, no further charging takes place. So charge transfer takes place. Charge transfer takes place till they attain common potential. Right. So initially, the capacity across this, the potential drop is V. Now, what is the energy initially? I will write simply this one has half a C1 V square. What is U finally? C1 plus C2, half C1 plus C2 V common square. V common square. This can be written as, V common is V common square, right? Uh, V common is a half C1 plus C2 Q by C1 plus C2 whole square. This you can write as Q is nothing but C1V. C1 square V square by 2 times C1 plus C2. That is finally stored. So now I will take U initial minus U final. This is nothing but half C1 V square minus half C1 square V square by C1 plus C2. In this, half C1 V square if you take common minus C1 by C1 plus C2. So therefore, loss in energy is nothing but half C1 C2 by C1 plus C2 into V square. In this also, you will face a loss. What about the charge transferred? Charge transferred is nothing but Q C2V, V common. So therefore, this is nothing but C2 by C1 plus C2 times Q, or C1 C2 by C1 plus C2 times V. This is the expression for, tell me, charge transferred. So you can charge a capacitor in two ways. One, by connecting it across a battery, or by connecting it across already charged capacitor. Till this point, any student having doubt? Pakka? Right. Next. Everyone try to solve this question. Try to solve this question. A parallel plate capacitor. Just go through that. See this question, parallel plate capacitor has a capacitance C. The charges of the plates are Q minus Q. Find. See, forget about this chapter. Earlier, when we had this chapter, we have done the questions like this. Wait 1 minute. 1 minute. We will assume the entire arrangement as one single plate. What is the total charge of the system in that case? Minus 2Q. That will be distributed equally on outside surfaces of the system. Step 1. Now you conserve the charge. Now here it should be plus 2Q and here it should be minus 2Q. Now they are separated by D. Now you know there is electric field E here. Can you please help me in writing the electric field? Gauss law states It is 2q by epsilon naught A. Any doubt in this? Pakka? Not q by epsilon naught A. It is 2q by epsilon naught A. So what is the potential difference? E into T. E into D. So therefore, this is 2q by epsilon naught A into D. Right. Right. So what is the charge flown if they were connected? Now, potential difference I have given clearly, right? Now, what is the energy stored in this system right now? Half, half C delta V square. Yes or no? Half C epsilon naught A by D into 4q square by epsilon square A square D square. Yes or no? Remember, this is the energy stored inside. I'll take U naught. U left, there may be some energy. U right, there may be some energy because there is a field due to those charge distributions. So the total energy U is UL, UR plus this part. 2q square by epsilon naught A T. That's the energy at this point of time. Now, when you short these two plates, what's happening? There won't be any charge and potential remains the same. Finally, you will see only a charge minus q this side, a minus q this side, and electric field inside becomes 0. So U initially is this. U finally is UL plus UR plus 0. You lost actually. So what is the energy lost? 2q square by epsilon naught A into T. Any doubt till this step? Everyone. So charge flown, right? This is potential difference between the plates. Charge flown if the plates are connected. Energy lost by the capacitors, right? Charge flown if any plate is earthed. Now, how to understand this particular question? I mean, easy questioning me, uh, like after second step, after third step, or after fourth step, or in what way? That's what I just want to check with. For example, third part, energy lost by the capacitor in third case, right? Charge flown if any plate is earthed. Now, what is available for you? Now you're is that after connecting to earth? If this is the case, nothing will be there. The entire charge will goes to 0. So what is the charge going to earth in that case? Minus 2. In that case, the amount of charge that goes through the ground is minus 2q. Minus 2q from right side plate to earth. I hope I have given you sufficient clarity on this. Clear? Mahant. Right. Sure? Right. This is a basic question which is related to the previous content of electrostatics. Next. Why don't you try this? two long straight wires with equal cross-sectional radii A are located parallel to each other in air. This is a Pathfinder line, irido question. The distance between their axes is equal to B. Like previously, you have compared with the spheres. Now they have given cylinders. Any doubt till this point? Paka? Right. So only for your understanding, I am drawing a portion of that. This is not the complete portion. I'm just showing a portion of that. You have given positive charge to air and negative charge. That's how we start. That is the basic definition of capacitor. Emma, yes or no? We start with this definition. Right. May I ask you a question? Now you have given a positive charge here, somewhere here, at a distance of x from the left side, at a distance of b minus x from the right side. What is going to be the electric field? If it is only due to the positive side, I think you recall this formula. We have recently done electrostatics. Lambda by 2 pi epsilon naught x. This is rightwards. E minus is lambda by 2 pi epsilon naught p minus x rightwards. Why leftwards? Negative charge. So E net, what is E net? E net is E plus plus E minus lambda by 2 pi epsilon naught 1 by x plus 1 by p minus x. This is the electric field. I assumed between the region of the two cylindrical charged wires. Now, what is potential difference? Potential difference is integral E dx here. E dx limits, you are moving it from this surface to this surface. A to B minus A. From this axis, this surface is at a distance A, and this surface is at a distance B minus A, because B refers to axis distance. So, by doing this, you will have A, B minus A, lambda by 2 pi epsilon naught, 1 by x plus 1 by B minus x dx. Remember, this is lambda by 2 pi epsilon naught. You know, 1 by x dx is a log. Log E B minus A by A. And this will become minus log E A by B minus A. Agreed? Here, substitute. Now, this can be written as lambda by 2 pi epsilon naught times 2 times log E B minus A by A. Don't forget, this is potential difference. Now, this can be written as lambda is equal to pi epsilon naught by log E B minus A by A times delta V. And this part is called as capacitance. No, not totally. That is the charge per unit length, the left side. So this will become capacitance per unit length. Any doubt in understanding this? Pakka? Right. So thereafter, we will proceed further. There are two more questions. Some maturity is required to solve that. So I'll do it in second or third class related to the same. Next. Are we clear about this question? Pakka? Any doubt? Sure? Right. As someone was trying to ask. Yeah. When I am moving it from high potential to low potential, why minus sign? Right. Next. Hold on. Two capacitors. C1 is equal to 2 microfarad. C3 is equal to 3 microfarad. Are charged separately to potential 20 volts and 10 volts respectively. The terminals of the capacitor C1 and C2 are marked as, hold on. This is your C1. This is C2. For a while, say you have some provision for switch here. Right. And terminals are labeled as A and B. And C2 are C and D. Now A is connected with C and B is connected with D. Now please remember plus plate, minus plate, plus plate, minus plate. And remember initially this is of potential V1 and this is of potential V2. Till this point, any doubt? So how long the charge flows? Charge will flow till they attain common potential. Not necessarily they should have same charge. Remember. So what is the expression for common potential? This is the total charge initially on observed portion like this. An observed portion like this, C1 V1 plus C2 V2. And this is equal to C1 plus C2 times V common. So therefore, what is the common potential? C1 V1 plus C2 V2. So the common potential is C1 V1 plus C2 V2 by C1 plus C2. So you will have some common potential now. This will become 2 into 20 plus 3 into 10 by 5. That is 40 plus 30, 70 by 5. So what is this going to be? 14 volt. That is the common potential difference across the plates. Now, what is the final charge? What is the final charge? Final charge, you can see Q1 dash is C1 V common. What is C1 again? 2 microfarad into 14, which is nothing but 28 microcoulomb. Q2 dash is C2V common, which is nothing but 3 into 10 power minus 6 into 14. 3 14s. 42 microcoulomb. 42 microcoulomb. Clear? Right? Total మీకు వచ్చిన 70కి సరిపోయింది చూసుకోండి కావాల్సి వస్తే. Numerator of the first case. Right. Find the final. How much heat is produced in the circuit? Please remember loss. Half C1 V1 square plus half C2 V2 square minus half C1 plus C2 V common square. Solving which you will get C1 C2 by C1 plus C2 into V1 minus V2 whole square. Remember, this is also an important model formula as far as mains is concerned. So this will become half into 2 into 3 by 5 into potential difference. 42 minus another potential difference is 10. 10 square. So this will be 300 by 5. How much is this? 60 microjoules. Don't forget capacity is in the unit of micro. 60 microjoules. That is the loss. So if two capacitors initially charged with like plates connected, remember in this, when like plates connected, so what is the expression for loss? Half C1 C2 by C1 plus C2 into V1 minus V2 whole square. What is the expression for charge transfer? What is the expression for charge transfer? C1 C2 by C1 plus C2 times V1 minus V2. Previously it is only V1. Now V1 minus V2. Suppose when unlike plates are connected, in that case, the expression will change to the form V1 plus V2 whole square, C1 C2 by C1 plus C2 times V1 plus V2. Boys and girls, if you have any doubt, please ask me. Clear? Pakka? Right. Next, take this model. Take this model. You take first model. In the figure, different capacitors are arranged. Find the equivalent capacitors across A and B. Now you take the first part. You focus first on this part. I know you want across AB. So first focus on this part. Now in this part, 6 series. What is the effective capacitance? 6 series. 3 microfarad. 3 parallel. 3 parallel. 6 microfarad. So therefore, the equivalent part of this goes to be 6 microfarad, 6 microfarad, and 2 microfarad across AB. Again, 6 series, 3 2 parallel later on, 5 microfarad. So totally this will tend to 5 microfarad. Across AB, it is going to be 5 microfarad. Remember the entire combination, this entire combination become 3 microfarad. And that is in parallel with 2 microfarad. 2 microfarad. 5 microfarad. Right. Next case. The next question. Yeah, tell me. So where do your focus need to be? 9999. 3 microfarad. Don't add. Don't get confused. Capacitor series is different. Unlike resistors. 999. 3. 3 6 parallel. 9. 9999. 3. 3 6 parallel. 9. Again 999. So therefore, in this case, effectively across AB, this is going to be 3 microfarad. I'm just asking you one straight question. How many required the second part of the question to be discussed once again? Honestly, raise your hands. First part is required. First, I'm asking about second part. Anyone in this class who would like to question? Who is that? What is your doubt? Are you confused? Are you convinced with this arrangement as 3 microfarad? Now, what is going to be this arrangement? 3 plus 6, because 3 and 6 are in parallel. 9 microfarad. Now, again, this entire thing is a 9. You have two such nines in series. Again, this will become 3 microfarad. So what is the next net amount of this? 3 microfarad. 3 microfarad in parallel with 6 microfarad. What is that you are going to be? 9. Which means the entire portion is going to be 9 microfarad. 999 series. 999 series are 3 microfarad. Right. Whereas you do the same problem here. 6 6 series. 3. 3 3 parallel. 6. Now this entire thing is 6 plus again 6 in series. 3. So the entire upper portion is 3 microfarad. That is in parallel with 2 microfarad. So total capacity is 5 microfarad. Any confusion in this? Very clear? Right. Now do this. Now do this. For this, I will do a small help for you. You label this as already A. You label this as A. You label this as a small a. You label this as a small b. Right. Okay. Are here B and A are at same potential? Yes or no? So therefore, what is that? You need to write A and B one line. Small a and B another side. Now, A to B, there is nothing. Not. A to A, you have one capacitor. Right. B to A, you have another capacitor. Like, I just want to throw some light without ever confusion. This is the capacitor. This is the capacitor. And one more point, B to B, capital B to small b, you have one more capacitor, right? Which I can show here. Here. So, did I cheated you? Did I miss any capacitor? Boys and girls. Now, how are all across AB? They are in parallel. So, therefore, effective capacity is 3C. This is how you should you should convert the condition. Clear? Now, why don't you try the next part? Why don't you try the next part? Now, here A and P are same potential. A and P are same potential. You know how I will rewrite this? You know how I rewrite this? C, this I'll connect over to here. The entire line is A. Here is your P. Here is your P. I didn't do any cheating part here. Please try to understand. Here, this capacitor I have shown here. Do you object? Then the question is done. Now, how you will write this? C and C. This will become 2C. And again, that is in series with C. And again, you have a C here. And this is A and this is B. 2C, 2C, 2C series. So this will become 2C by 3. And niche you have C. So effectively, in this case, this will become 2C by 3 plus C, so which is 5C by 3. Any doubt, boys and girls? Any doubt? Here, work at this. There is no capacitance at all in that arrangement. No capacitance at all in that arrangement. Why, I will explain. If you rewrite this, that's okay. But whereas you have shorted both the ends, this is called shorting. You have connected A to B straight away with the conductor. I am not cheating you again. I am showing the path. You have shorted. Because of that, nothing is left there. Nothing is left there. So therefore, what you should comment here in this particular arrangement? Tell me. You cannot hold any charge there. Why? Whatever the charge you give to A, without being storing, it reaches B. Because the charge flows from high potential to low potential. What will be stored there? Nothing. So therefore, what will happen is the equivalent capacitance in that case is like a conductor. Entire arrangement is a conductor. So this conductor will not store any charge. So the capacitance is 0. The capacitance of the arrangement is 0. Right. Next. See, for today, I'll stop over here. For tomorrow's class, we will continue further.